In the last lecture, we focused on the elements of matter and the subatomic particles that make them up. In this lecture, we focus on how these subatomic particles behave, which just might turn our entire conception of what they are on its head. Are they particles? Are they waves? Can they be both at the same time? We call the behavior of particles quantum mechanics. Quantum because their properties only change in discrete amounts. And mechanics because we're really interested in what it is that they're doing. One of the most important scientific discoveries in this or any area began, as is often the case, with a controversy. In the 17th century, physicists were particularly interested in understanding the nature of light. Curiosity on the subject actually extends all the way back to the time of the Greeks, when Aristotle first suggested that light travels more like a wave in the ocean than like a stream of discrete particles. But in the 17th century, two great minds proposed opposing theories. Christian Huygens suggested that light is made up of waves, and Isaac Newton insisted that it consists of particles. Newton was a giant in science, even in his own day, and although he himself expressed some doubt about the veracity of his theory that light is a stream of particles, it remained widely accepted until the early 1800s. That's when Thomas Young proved him wrong. Sort of. Young's experiment is so important that Richard Feynman has been quoted as suggesting that all of quantum mechanics can be derived by carefully considering its implications. So it's worth taking a few moments to understand it. The experiment involved three things: a light source, a thin barrier with two vertical slits, and a photographic plate. Let's say we place the light source in front of the barrier and point it towards the plate. As the light source sends out light, the barrier dictates where it goes. It must pass through the slits, and the photographic plate captures where it ends up. The brighter the image on the plate, the more light has reached that point. Now, if we turn on our light source and cover one of the slits, we see a single line of light on the photographic plate corresponding to the remaining open slit. Doesn't matter whether that slit is the right or the left one. But when both slits are open, Newton's theory predicts that we'll see two vertical lines of light, each corresponding to one of the slits. If you think of light particles as tennis balls, and the slits as just large enough to let them through, we'd see tennis balls hit the plate along two vertical lines. But Huygens' theory makes a different prediction. If light acts as a wave, undulating up and down, then when it passes through the slits and gets separated, the two waves will interact with each other. In places where the peaks of the waves hit each other, you'll see a greater concentration of light. And where the valleys overlap, you'll see less light. But there will also be times when a peak and a valley hit each other, canceling each other out. So if light travels as a wave, you'll see a different pattern on the photographic plate. It'll look like a whole series of vertical lines, not just two, of different brightnesses. The brightest ones showing where the two peaks coincided, and the dark areas where they canceled each other out. We call this sequence of light and dark bands an interference pattern. When Young turned on his beam of light, he saw precisely this interference pattern, not the two simple lines that we would see if light behaved as a particle. And so Newton's theory was proved wrong. In order to predict how the waves in an interference pattern will interact, we need to know their wavelength. That is, we need to know how far apart the peaks and valleys of the wave are. The further apart they are, the longer the wavelength, and therefore the lower the frequency. Longer wavelengths mean that for a given peak, it takes more time to reach the slit, which is the same thing as saying that the frequency with which it hits the slit is lower. Now, waves with lower or smaller frequencies and longer wavelengths have less energy. So energy and the wavelength of light are related. That all seems to make sense, but towards the end of the 19th century, science was in a quandary over the subject of energy. In 1900, another scientist named Max Planck made a guess that would eventually win him the Nobel Prize in 1918, and would question just how wave-like light really is. The problem that Planck set out to tackle can be traced back, in one sense, to the kitchen. It seems that a bunch of physicists and mathematicians used their well-established formulae to try to calculate how much energy is inside an oven when it's heated to a certain temperature. Sounds like a fairly straightforward and somewhat boring calculation. But the answer that they got was shocking. No matter what temperature was reached inside the oven, whether it was 200 degrees Fahrenheit or 450 degrees Fahrenheit, the total energy in the oven was calculated to be infinite. What? Surely that's impossible. My oven doesn't contain more energy than the sun, even when I'm cooking Thanksgiving dinner. Of course, the group realized the calculations must be wrong. But it wasn't until the year 1900 when Max Planck made a fortuitous guess as to why they were wrong, and the problem found a solution. The field of quantum mechanics was born. Planck's guess, in a nutshell, was that energy doesn't operate on a continuum. It comes in units. Now, to understand that solution and its far-ranging implications, I want to borrow a thought experiment from physicist Brian Greene, which he describes in his best-selling book, The Elegant Universe. It helps explain the nature of energy and of light as well. Now, imagine you live in a cold warehouse with an infinite number of other people and a very stingy landlord. Your landlord charges each person in the warehouse a certain amount of money depending on the temperature at which the thermostat is set. If it's set to 50 degrees Fahrenheit, each person needs to pay $50. If it's set to 68, each person pays 68, and so on. You quickly realize that since there's an infinite number of tenants, your landlord is getting very, very rich. In fact, he'll earn an infinite amount of money if you turn on the heat at all. Now, you're not particularly fond of your landlord. He doesn't keep the place up, repairs aren't attended to, and he kicks people out for no reason. So you read your lease very carefully and you stumble upon a loophole. Since the landlord has an infinite number of tenants, he's a very busy man and relies on the honor system for payment. Oh, and he doesn't give change. So those people who can pay exactly what they owe do so. Everyone else pays only as much as they can without needing change. This contractual provision gives you an idea. You organize all the money in the warehouse in the following way. One person holds all of the pennies, another all the nickels, someone else holds all the quarters, another dollar bills, etc., all the way through the denominations, including $1,000 bills and higher. Now remember, you have an infinite number of roommates, so someone must have a $1,000 bill. Then you crank up the heat until the thermostat reaches a balmy 80 degrees Fahrenheit. Finally, warm and cozy, you await the landlord's arrival. When he arrives, his face lights up as he thinks about all the money he's about to collect from his comfortable tenants. First, you send out the person carrying pennies, who diligently counts out 8,000 coins for $80. Next, the nickel carrier turns over 1,600 nickels. The person with the dimes gives up 800. Then the person carrying quarters counts out 320. The person holding dollar bills gives him 80, and the person with $5 bills turns over 16. The $10 bill carrier gives him 8, and the person with 20s hands over 4. Now it gets interesting. The person carrying the $50 bills only hands over 1, since the second would require change and no one else needs to pay, because their denominations exceed the required payment, necessitating change. The the landlord leaves with a meager $690 instead of the infinite sum he was expecting. You celebrate by turning up the heat yet another notch. Planck's guess solved the problem of the infinitely energetic oven in the same way, by proposing that energy comes in lump sums like money. There is some fundamental energy denomination, and then energy can increase only by multiples of that initial sum. No fractions are allowed. Just as you can't have half a quarter, you can't divide the energy beyond its denominations. But how are the values of these denominations determined then? Planck suggested that the minimum energy that a wave can have is determined by its frequency. That is, how often the peaks and valleys alternate. And as we saw a minute ago, this relationship is inversely correlated. That is, the smaller the frequency, or the longer the wavelength, the lower the minimum energy. Waves with shorter wavelengths have more energy. If you take a rope and create a wave with it, it takes less energy to make a slow, undulating wave with a long wavelength, and more vigorous work to create shorter wavelengths at a higher frequency. And this principle applies to light as well as to heat. So the minimum denominations of light correspond to the frequency of light. That is, waves come in specific wavelengths. It's quantized. But why would that be so? We've talked about how light travels in waves, as the double slit experiment demonstrated, and we've talked about how Max Planck won the Nobel Prize for postulating that the energy in the waves comes in lumps rather than on a continuum. The next question is, what do these two things have to do with each other? And for that, we need to turn to Albert Einstein, because Max Planck couldn't tell us why energy is lumpy. What Planck showed is that the table manners that your grandmother taught you are written into the very nature of energy. You can't leave the table until you've eaten everything on your plate. You either eat all of your dinner or none at all, but you can't just eat the mac and cheese and leave the broccoli behind. Planck's discovery may have won him the Nobel Prize in 1918, but he didn't tell us why energy behaved this way. It was Einstein who provided the why, and he won his own Nobel Prize for it in 1921. To better understand Einstein's explanation, it's helpful once again to use an analogy. Let's say that you live in a city where the parking meters only take quarters, and they give out parking times in 8-minute increments. For each quarter you put in, you get 8 minutes of parking. Let's also imagine that you have pennies, nickels, and dimes, but the meter, again, only takes quarters. No matter how many pennies you put into the meter, the time gauge doesn't move. But if you only need to park for 5 minutes, you still need to use a whole quarter and pay for 8 minutes. Now, let's say that you teach yoga classes that are 45 minutes in length. For each class, you need to pay for 48 minutes or use 6 quarters, even though you only need 45 minutes. So even if you only use the meter for 45 minutes, you still end up paying in increments of 8 minutes. Einstein figured out that energy has the same properties as the parking meter. It can only be increased in certain increments. And that's because the energy is triggered by something akin to putting a quarter in a meter. It's the ejection of an electron from a metal or other atom. Einstein's insight as to why energy is lumpy is based on his explanation of something called the photoelectric effect. The photoelectric effect describes the observation that when you shine a light on certain metals, they eject electrons. You'd think then that the more intense the light, the more electrons are ejected. But what controls whether or not electrons are ejected is the wavelength of the light, not its intensity. Light of different wavelengths looks to us as though it has different colors, with red light having the longest wavelengths and violet light the shortest. With our parking meters, it's not the total dollar value of cash that we put in, it's only the number of quarters that determines how long we have to park before we get ticketed. Einstein suggested that we should think of light as a stream of tiny packets, eventually called photons, each with an energy value that is proportional to the wavelength or frequency of the light wave. If the light beam's wavelength is too long, and its frequency therefore is too small, the photons in that beam won't have enough energy to knock out electrons. No matter how many pennies you put into the meter, the dial won't move. But as soon as you put in a quarter, you get 8 minutes, or you eject 1 electron. Even if you only need 5 minutes. More quarters means more 8-minute increments, but the dial only moves by 8 minutes, no matter how quickly you put in the quarters. Einstein showed that Planck's guess that electromagnetic energy is lumpy results from the fact that waves are composed of little bundles, photons, or quanta of light. Just like water is made up of molecules, and therefore waves in the ocean can be broken down into particles, so too is light made up of photons. So Newton and Hurrens were both right. Let's review what we've just learned for a minute. Newton suggested that light moves like a stream of particles. Hurrens argued that it travels more like a wave. The photoelectric effect, in which light can displace electrons on a metallic surface, demonstrate that light has particle-like properties. But Thomas Young's double-slit experiment demonstrates that light also shows interference effects, as would be predicted if it moved like waves. So light has both particle and wave properties. This is a hard concept to come to grips with, and Feynman's assurance that nobody understands quantum mechanics gives us a little bit of relief. We're not alone in thinking that all this stuff is a bit weird and hard to believe. We can talk about wave-particle duality as if it's a fact. We can use this information to generate equations and models that accurately predict the behavior of quantum things. But truly understanding how this is possible, given our experience of a predictable, solid world of matter, well, that's another story. But let's do our best. To understand wave-particle duality better, let's consider how we would go about determining the location of a particle that is also a wave. Electrons are particles, as we know from the last lecture, but they also behave like waves. So how can we tell where they are in space? The answer to this question lies in the ideas of Austrian physicist Erwin Rudolf Joseph Alexander Schrödinger. It was Schrödinger who first proposed a famous thought experiment to illustrate one of the tenets of quantum mechanics, that if you put a cat into a box along with some radioactive substance, the cat is both alive and dead at the same time. We'll get to that conundrum when we cover quantum physics next. But Schrödinger also suggested that the wave-like trajectory of electrons should be thought of as a smeared-out electron. If you take blueberry jam and smear it on toast, some of it is here and some of it over there. But this description wasn't particularly satisfying because we never see bits of electrons. They are either whole or not. So in 1926, German physicist Max Born took this idea one step further and suggested that we think of the wave of electrons more like a cloud of probability. In spots where the wave's magnitude is large, to be precise, it's the square of the magnitude, but let's not worry about that for now, there is a high probability that the electron will be found there. Where the magnitude is small, we're unlikely to see it, but it's still possible. Now, we're familiar with probabilities as they apply to certain things that are uncertain, like the weather, when we're trying to predict it, or the sex of a baby before we know it for certain, or the outcome of a baseball pitch before the ball is thrown. But each of these cases represents a situation in which there is information missing. If we want to predict the weather, we need only to wait until the appointed time to find out what the weather actually is. Just like we need to wait until the baby is born to be sure of its sex, or watch the pitch land to know whether it led to a strike, a ball, or a home run. But in the case of electrons, quantum mechanics, as it stands today, suggests that we can never know exactly where the electron is at a given moment in time and how fast it's moving. This is a little weird. This paradox was captured by German physicist Werner Heisenberg in his famous uncertainty principle. We can't ever know definitely where an electron is and where it's going, or more precisely, how fast it's going. The more precisely we define its position, the less well we can measure its velocity and vice versa. Even Einstein found this notion unappealing, famously quipping, "God does not play dice with the universe." He thought there was still some information missing, that maybe we could fill in the missing parts of the equations. But time and time again, Einstein, despite his genius, and just like every physicist before him, has been proven wrong, at least on this point. Richard Feynman, my own personal favorite physicist, demonstrated that Heisenberg was right. We can never know both where an electron is and how fast it's going, and therefore we can never predict where it's going to be next. How did he do this? Well, simply by trying to locate the electron. How do we find a single electron? Well, one way is to shine a light on it, to literally bounce photons off of it and measure the trajectory of the photons and then extrapolate back to where the electron must have been. Let's try to find the electrons as they pass through the slits of the double slit experiment. Now, when we try to do that, by shooting photons at the electrons as they pass through the slits, we find that we end up altering their trajectory and changing the outcome of the experiment. Think of electrons as tiny paper airplanes flying through the air. To find them, we need to bounce something off of them like a raisin. But when the raisin hits the paper airplane, the plane shifts its trajectory and ends up in a different place than it would have been had we not thrown raisins at it. No matter how gently we probe the electron to find out its location, we still affect its movement. And we know that the movement is affected because the interference pattern that we expect to see on the photographic plate changes. This interference pattern is in effect a measure of momentum. So what does Heisenberg's uncertainty principle and Feynman's experiment tell us about the actual structure of atoms, or the elements of matter? Well, electrons are bound to the nucleus by the electromagnetic force. They are attracted to its positive core. And now we know that their placement around the nucleus is best described by a cloud of probabilities rather than any specific orbital route. Particle waves are waves of probability. We still don't really understand this duality of light, but despite its mysterious nature, we have figured out ways to use it to our advantage. Arguably, the most widely used application is the invention of the laser, or light amplification by stimulated emission of radiation, laser. So how do lasers work? Well, very simply, when an electron moves from a high energy state to a lower one, from one orbital shell to another, a photon is emitted. So light, essentially, is the movement of electrons between different energy states. Let's look more closely at this idea by seeing how lasers work. Stimulated emission happens when an incoming photon stimulates the electron to change energy levels and emit another photon. Then the new photon joins the incoming one exactly in the same phase. That is, their wavelengths line up like horses jumping over obstacles at exactly the same time. They're in sync. We say that the two photons are coherent. This coherence is a fundamental property of lasers and underlies their power. Because the photons are traveling in the same phase, we can control where they go by making very small slits or openings and restricting their movement. And because all the light in a laser beam can be restricted to a small area, the intensity or power per unit area can be very high. Lasers that produce light are technically optical oscillators rather than amplifiers, the word that puts the A in laser. So really, most of the lasers we use are actually losers. Though the term laser has become so intertwined with lasers that produce light that instead of introducing a new term, Optical amplifying lasers are called laser amplifiers, even though this nomenclature is redundant. But who wants to be called a loser? And that's just semantics. Let's get to the meat of the matter. Sometimes an electron jumps from one shell to another, from a lower energy state to a higher one. When it's at a lower level, it's more stable, closer to the nucleus. And because the electron is closer to the nucleus, the binding force holding it close is greater. These rogue electrons eventually have to move back down to their original lower states. And when they do that, they emit a photon of light. Now, not only do excited electrons emit photons on their way home, but they also encourage other nearby electrons to do the same. Remember the stimulated emission part? An incoming photon stimulates the emission of another photon with the same wavelength and direction. The architecture of lasers takes advantage of these properties. First, lasers need an initial power source to excite the electrons in the first place. And so different lasers use different sources of power, some greater than others, producing different beams. Lasers enclose the excitable electrons in a chamber with mirrors on both sides. That way, the light emitted by one electron bounces back and forth between the mirrors, eliciting the emission of other photons all the time. Once the laser is powered up and the photons are getting emitted, a little slit is opened on one end of the chamber, allowing only a small, coherent, intense set of photons to escape. They're all the same color, of course, because they have the same wavelength. And depending on the laser, the beam can be pretty mild, like the kind that we use to point to slides or with which we tease our cats. Or it can be the most intense beam of energy on the planet. Like the National Ignition Facility in Livermore, California, which houses the world's largest laser. At the NIF, as it's called, 192 laser beams travel 1,500 meters from the master oscillator to the center of a target chamber. In 5 millionths of a second, 4 million joules of energy are created. Just to put that into perspective, your microwave probably generates about 1,000 joules every second. What's the point of the NIF? Well, the goal is to create fusion energy, the same energy that powers the sun, and to use it eventually as a source of electricity. That would revolutionize the way that we power our society. Although fusion energy is still in development, lasers have already revolutionized our lives in many other ways. In medicine, we use lasers to correct our vision, to whiten our teeth, to remove scars and birthmarks. In soft tissue surgery, in no-touch surgical removal of tumors in the brain and spinal cord, and even to treat cancer with photodynamic therapy. We also use lasers to create holographs and 3D images, to cut, weld, drill, mark, and clad, for guidance systems and surveying, to store and retrieve data on optical discs such as CDs and DVDs, and to scan barcodes in just about every store you can think of. Theoretical physics is undeniably esoteric. Sometimes, efforts like the search for the Higgs boson can seem like a fool's errand in a world where poverty and suffering abound. But by understanding the nature of our world, even at the minuscule quantum level, we equip ourselves with the tools that may eventually allow us to eradicate diseases by developing better treatments, to eliminate poverty, environmental degradation, and competition for scarce resources by providing a cheap, renewable energy source, and thereby maybe even achieve world peace. Understanding how particles behave, how they can be both particle-like and wave-like, has already yielded many fruitful applications. And we still don't even know exactly how this dual nature works. I'm afraid we won't solve that riddle in this course, but in the next lecture, we'll explore some of the other strange and fascinating contradictions of quantum mechanics.